Hello and welcome. So let's continue with our series that where we are solving linear algebra questions from different paper, and right now we are with the statistics paper, and today what we will be solving is 2020 paper. So if you are new and if you are not following, then just for the info, what we are doing is we are solving in this series, in this particular series that you will also find into the playlist, that where we are solving the linear algebra question for data science and AI, right? And all the question that in lines with your syllabus with this DSAI, right? So just for info that we have already solved the linear algebra question from 2023 statics paper 2023, 2022 and 21. So today we will be solving 2020. Apart from that, we have also solved last 5 year question of mathematics, right? Not all the question, then we are solving only linear algebra. Probability we will see later. So today let's jump on to the questions, that whatever we have questions from linear algebra in 2020 statistics paper. So let me, okay, so I have already copied all the question here so that I have a space to solve the question. Right, so first question is this, that question number 28, and we have given for a real value of ABC, let m is equals to, so we have given this matrix M, then which of the following statement is true? So we will have to find the true statement, and it is 2 marks question. So let's look at this question. So the option, okay, so let's look first at this matrix. Okay, let me first, okay, now we have this matrix M, right? So let's check this first option, right? We can directly jump. Let's check this first option, that rank of M is 3. Now look at this matrix M. So if you look at this matrix M, then if you observe that this column and this column, so this second column is some multiple of column 1, right? So this second column is dependent on this first column, right? Yes, because if on the first column, if you multiply C with the first column, then you are going to get the column C2, right? So by looking at this, what we can say that since we have a column vector that is depending on some other column, so it will 100% sure that it will not have the full rank. So it is 3 by 3 matrix, so it will not have the rank 3. So this is 100% sure, so it can't be rank 3. So we can directly eliminate this option, that is option A is incorrect, right? So this is incorrect. Okay, now let's move to option B, right? So option B, we have to check if A plus B is equal to C, then M is diagonalizable for every B belongs to real number. So B belongs to real number, and we have given that if if A plus C is equal to 0, then M is diagonalizable for every B belongs to R. So B could be any real number. So what, a matrix can be diagonalizable when, if you know this, then only you can proceed further. Otherwise there is no magic to proceed further. So you will have to know when a matrix is diagonalizable. So matrix has to be a square matrix, and the matrix will be diagonalizable when it will have the independent eigenvectors, right? So we have nothing given here regarding the eigenvector. We have given just the matrix M. So we will have to look that by calculating the eigenvector we may have some info regarding the eigen vector, right? By calculating the eigenvalue we may have some info regarding eigenvector, right? So we can check it out. Let's calculate the eigenvalue, then maybe we will have some confidence about the eigenvectors, right? So let's calculate the eigenvalues. So what so to find the eigenvalue, what we are going to do is we are going to take this the m minus lambda times I, right? So first of all write this matrix. So what it will be, a minus lambda, and other will be as it is 1 c minus lambda, and here we will have 0 and bc 1 minus lambda, right? Now the next step, um, now the next step we have to find the characteristic equation. And how we find the characteristic equation? By taking the determinant, right? We will have to take the determinant of this matrix, that m minus lambda I. So you can expand this regarding this element, because in this column we have 2 0, so it is good idea to expand regarding this. So 1 minus lambda, and here we will have a minus lambda into c minus lambda, right? C minus lambda minus ac, right? So this is what we are going to get. So let's this would be equal to 0, the characteristic equation. So what we are trying to do is we are trying to find the eigenvalue, right? So 1 minus lambda, we can just multiply ac minus a lambda minus lambda c minus ac is equal to 0. So this ac will get cancelled. So what we will have 1 minus lambda. So we can take maybe lambda common. Here we will have minus a minus c, right, and equal to 0. Okay, I have left one more term, that ac and plus lambda square will be there, right? Okay, so here we will have lambda square and minus of lambda a minus of lambda c is equal to 0. So 1 minus lambda, and you can take lambda common, and here we will have 1 minus lambda minus a minus c is equal to 0, right? So from here you can find the value of lambda. That will be lambda 1 is equals to first eigenvalue is 1, and lambda 2 is equal to 0, and you will, and lambda is equal to lambda 3 is equal to a plus c. So these are the three eigen value, right? So, and if you look at this option 2, so option 2, that we have given that if a plus c is equal to 0, so what will happen? Lambda 3, it will be a plus c is equal to 0. So these two lambda are same, so these two eigenvalues are same, and corresponding to these two value of corresponding to these two eigenvalue, we will get the same eigenvector, right? So for three eigenvalue we will have eigenvector, and for these two eigenvalue we will have the same eigenvector, right? So we are not getting the independent eigenvectors, right? And initially what I told you, a matrix will be diagonalizable once we have all the eigenvector that is independent. And what we are getting from these two eigenvalue, we will get same eigenvector, right? So from here we can say that matrix M, if this condition is correct, A plus C, then matrix M is diagonalizable. No, so this option is incorrect, right? Okay, now let's check this option 3. Let is option C. What it is saying that M has a pair, so you will have the pair of orthogonal eigenvector. So we can deduct this point C also from here. So M has pair of orthogonal eigenvector for every A, B, C belongs to real number. So you will have to make focus on this point, that pair. Can we get, can we, how many eigenvector we are going to get from how many distinct eigenvector we are going to, or independent eigenvector we are going to get? Two for sure, right? One for this lambda 1 is equals to 1, and two from these two, right? And that will be the same. And whatever, let's suppose we got some e1 vector, and from here we will got e2. So these two pair of eigenvector will be orthogonal, right? So yes, we have pair of orthogonal eigenvector for any value of ABC that belongs to real number, right? So this option C is correct. Now you can check this option D also. Now to check this option D, if B is equals to 0 and A plus C is equal to 1, then M is not idempotent. So idempotent matrix. So first of all, you will have to know about the properties of the idempotent matrix. So how you can check, what you can do, if you do M square is equal this multiplication, and if you are getting again this M, then this will be a idempotent matrix, right? You can check it. Let me check. So let's do the multiplication. So here we have A1 B and AC C BC and 0 0 1. So we will have to multiply you. So you can multiply. So here, so it will be a square right. So a square plus AC also. Okay, what I am doing, we will have to consider this also, right? B is equals to 0 and A plus C is equals to 1. So let me consider this point also, then only we can check. Okay, so let me first erase this one, we don't need. So first of all, let's consider these 2 points. So we will have to put this B is equals to 0 and A is equals to minus C. So you can put at this equation. So at the place of A, so at place of A, let's put 1 minus C, right, from here, and here we will have 1, and at place of B let's put 0, and at place of A let's put 1 minus C, and here it will be 0 and 0 0 1. Now we will have to multiply with the same matrix. So 1 minus C 1 0, C times 1 minus C 0 0 0 1. Now if we get the same matrix, then we can say that it is idempotent matrix, otherwise we can go for MQ. So let's check. So first we will do the multiplication like this. So it will be 1 plus 1 minus c, right? So we can write 1 plus c square minus 2c and plus c minus c square, right? So this is c square. Okay, now here we will have c1 minus c square. That means so what we can do here, 1 minus c whole square, so c plus c cube minus 2c square, right? And plus here we will have c square minus c cube, and what we are going to get, the third column is 0. Now we will do for this, that what we are going to get is 1 minus c and plus c, and here what we are going to get is c minus c square plus c square, and here what we are going to get is 0, I think. Yes, 0, yes. So here it will be 0, and here it will be 0, and here it will be 1. Now we have cancel. So what we are going to get, 1 minus c, right? Yes, and this cq will get cancelled, and here we will have c minus c squared. So we can write c times 1 minus c, right? So c minus c square, correct, 0, and here this will get cancelled, and here we will have 1, this will get cancelled, here we will have c 0 0 1. So you see that these two matrices are same, this one and this one. So this one is the idempotent matrix. So this is idempotent, and we have given in the option not idempotent. So according to that, this option is incorrect. So for this question number 28, option C is the only correct answer. Okay, now let's move to next question. Today we will not have much question, so I think 2 or 3 question is there only, and one question was there, but that was related to some complex matrix, so that was not in the syllabus of data science. Okay, now let's move to this question number 29. Let M be a 4 by 4 matrix with this as the minimal polynomial. So we have given this minimal polynomial, and then which of the following statement is false? We will have to look at which of the following statement is false. So we have given this minimal polynomial, so we can comment about the eigenvalue, and from the here we can say that eigenvalue will be 1 or 3, so that is for sure, right? So option A is the correct, but we will have to find the false. The algebraic multiplicity of eigenvalue 1 is 3. So we will have to find the algebraic multiplicity, right? And what is, so we have two terms that you have, algebraic multiplicity, and one is geometric multiplicity. And what is geometric multiplicity? So geometric multiplicity is the dimension of your eigenvector. So what you will do, you have given a matrix, you will find the eigenvalue and you will find the corresponding eigenvectors. Now what you do, you put all those eigenvector into a column vector, right? And you find the dimension of this matrix, that will be the geometric multiplicity. Whatever dimension you will get of this matrix, that is of eigenvector, then that dimension will be called geometric multiplicity. And here we will have to find the algebraic multiplicity. And what is this algebraic multiplicity? In minimal polynomial, if I ask you, if you have find the minimal polynomial, and if I ask you that give me the geometrical multiplicity of this eigenvalue 1, so you will look at here and you will look at the power of this. So from this minimal polynomial we can comment about the algebraic multiplicity, and for this eigenvalue 1 the algebraic multiplicity is 2, right? So this option is false. Yes, it is false. So according to that, according to question, this is the correct answer, right? So m is not diagonalizable. Obviously m will be not diagonalizable because we have the repeated eigenvalue, right? So lambda 1 is equals to 1, lambda 2 is equals to 1. So corresponding to that we will get the eigenvector that will dependent to, we will get the same eigenvector for this eigenvalue, right? So we will have some eigenvector that is dependent, right? So we cannot diagonalize this matrix M. So this statement is correct, but according to question we will have to find the false statement that we have already got, that this is this B is the correct answer. But we are looking at the options, and let's look at this option D. Trace of M is 8. So here that x minus 1 square and x minus 3 square, right? So from here what we will get, lambda 1 is equals to 1, lambda 2 is equals to 1, and lambda 3 is equals to 3, lambda 4 is equals to 3. So 3 plus 3 6, and plus 1 7, plus 1 8. So this is also correct. So according to question we have to find the false statement. So option B is the false statement, and this is the correct answer. Okay, now we have one more question. So let's look at this question number 1. Okay, so so we started with 21 28. Okay, so so this question is, let M be 3 by 3 non-zero idempotent matrix. Let I3 denote 3 by 3 identity matrix, then which of the following statement is false? Okay, so we have, so the point is that you need to know about the properties of idempotent matrix. So if you know the properties of idempotent matrix, then this question is based on that properties only. So you can have a look here. So these are the properties of the idempotent matrix. So every idempotent matrix is a square matrix. All idempotent matrix are singular matrix apart from the identity matrix, and the determinant of idempotent matrix is either 1 or 0. So you can look at this, and from here you can easily get which option is correct, right? So if you look at this question, so all we have given is only the properties of this idempotent matrix. So this we have to find the false one. This one is correct. The eigenvalue of M will be either 0 or 1, so this is correct. And for idempotent matrix, the rank of matrix is the trace of the matrix, that is sum of the diagonals. And this option 3 is false one, because what it is saying that that identity minus some idempotent matrix will be a idempotent. Is this correct? So we cannot be sure. That's right. So according to that, option 3 is the false one. And this statement 4, so if you look at this property, the last property, what does it say? The following. So there is the relation between involuntary matrix and this idempotent matrix. So from here, between the relation between the involuntary matrix and with the idempotent matrix, you can get this option 4. So this is also the correct one, right? So for this question, option 3 is the false one, and apart from that, all these are correct. So you can look at this properties of idempotent matrix. You can look at this properties of nilpotent matrix, and you can look at uh, this matrix, that is the involuntary matrix. So these are the special kinds of matrix. The properties of these kind of matrix you need to have in your mind during the examination, right? So that is all. We have only 4 questions, but one question was based on the complex number in matrix. It was from the complex space, so I haven't considered that example since it is not in our syllabus. So that is all. We have only 3 questions. We will look next paper, that is 2029 in this video. That is all from my side. Thank you.